Knowing the mechanisms for acetal formation and imine formation is so powerful because it explains reactions that are really similar with other nucleophiles. So for example, with acetal formation, we saw how you could have a ketone and you could treat it with two equivalents of an alcohol, something like this, and that gives you an acetal. So those two oxygens here can bond to the carbonyl carbon, and they're still connected by that chain. And we went through the mechanism for that several times in the videos for acetal formation. Well, right underneath oxygen on the periodic table is sulfur. You have oxygen, and just below it, so a bigger atom, but the same number of valence electrons, is sulfur. And so sulfur forms similar compounds as oxygen does, and they have similar chemistry. Sulfur is a better nucleophile, it's more polarizable, and it's not as prevalent on Earth's surface or in general in the universe because it takes a longer amount of time for the universe to smush enough protons together to get that atom. The prevalence of elements in the universe decreases as you go down in the periodic table because it takes longer for stars to make those elements. But aside from that, sulfur has really similar chemistry to oxygen. And actually, through the same mechanism that we drew for acetal formation, you could add these dithiols, and remember an SH is a thiol. This is an alcohol with an OH, and SH is a thiol. So you could add those two equivalents of a thiol, and you could get this sort of sulfur equivalent of an acetal. It's called a thioacetal. The thio just is referring to the sulfur. Oops. So this top one was an acetal, the bottom one is a thioacetal. And the sulfur, the mechanism is really the same. So if you go back and watch the video for the mechanism of acetal formation, just replace all the O's with S's, and you would get this thioacetal formation. Now, thioacetals can be removed, they can be reduced. You can take the two bonds to the sulfurs, and you can replace those with bonds to hydrogens. That's what reduction means in organic chemistry. You take a bond to something that's electronegative and you replace it with a bond to a hydrogen. So you can replace that with bonds to hydrogens, and notice that normally you wouldn't draw those hydrogens. So if you do that, you really just end up with the carbon chain by adding a compound called rainy nickel. Now this is not rainy as in water coming from the sky. It's named after a scientist. And what this is a nickel aluminum alloy. So it's nickel and aluminum metal melded together, all the nuclei of those atoms trapped in a sea of electron dough, like blueberries in a blueberry muffin. And on the surface of that, it's very porous, so there are a lot of caverns and caves in this nickel aluminum alloy, and on that large surface area, with all those caverns and caves, there are hydrogen atoms adsorbed. So hydrogen atoms just ice skating on the surface of that metal. And when the hydrogens adsorbed onto this rainy nickel bump into this molecule, they end up kicking the sulfur off and replacing it. And so you don't need to know the mechanism for that for our class. But the result of using rainy nickel is desulfurization. You replace the bonds to sulfur with bonds to hydrogen. So those two reactions, thioacetal formation and reduction of a thiol, desulfurization using rainy nickel, that's what exercise 2029 is asking you about. And they're not asking you to draw the mechanism, they just want you to draw the product. So just for practice, let's draw the product of each step. So not just they're just asking for the overall product, but just so that we can visualize what each step is doing, let's draw the product of each step. So the first step, we have our acid catalyst, H+ in brackets. We've seen that as other things in acetal formation. We've seen TSOH, that's toluene sulfonic acid, or H2SO4, sulfuric acid. They're just catalytic acids. And then we're adding this special dithiol. You have two SHs at the end of this 2-carbon chain. So what ends up happening, you have the same carbon chain. What ends up happening after that first step is in the carbonyl carbon, instead of being bonded to oxygen twice, will be bonded to the 2 sulfurs. And the carbon chain in between them will still connect them. So you'll still have that carbon chain in between them. It's just instead of being bonded to hydrogens, they'll be bonded to the carbonyl carbon. So that's the result of the first step. The result of the second step is desulfurization. We saw that rainy nickel is that sort of gigantic ice skating rink where hydrogen atoms are adsorbed and floating over the surface of the metal, this very porous metal. So when you do that second step with rainy nickel, that nickel aluminum alloy, it just replaces, it replaces the bonds to sulfur with bonds to hydrogen. So you basically just take the sulfurs off. Now you're replacing it with bonds to hydrogen here. You could draw the hydrogens if you want, but you could also not have them there. Oftentimes the solution manual just wouldn't write them in. They're implied in the skeletal structure. So the overall major product of this whole process is this right here. That's what they're asking for. But I wanted to draw in what happens after each step just for some extra practice. So a similar thing happens with B. We just have a different carbon chain attached to the carbonyl. We have this aldehyde here. So if you want to practice with naming, this would be 2-methylbutanal. And when you do the first step, you add catalytic acid and this dithiol. When you do that, you replace the 2 bonds to the oxygen on the carbonyl, the 2 bonds to the oxygen on that carbonyl, you replace those with bonds to the 2 sulfurs. So 1 bond to one of the sulfurs, another bond to the other sulfurs. And notice the 2 sulfurs are connected by 2 carbons, so we're going to draw those in, 1, 2. And that's the step after that, thioacetal formation. Then you can use rainy nickel. That's that nickel aluminum alloy with a bunch of hydrogen atoms adsorbed on that very porous surface. And that replaces the bonds to the sulfurs with bonds to hydrogens. And notice, this is a skeletal structure, so you could just draw it without the hydrogens, and it would look like this. So you'd have 2-methylbutane as your product. Either one is fine for me. If you drew it this way, I wouldn't take any points off at all. They're the same structure, so both of those. So you could see how, once you know the mechanism for acetal formation, seeing how other nucleophiles, like sulfur, how those behave when they come into contact with a ketone is really straightforward because it's really the same. It's very, very similar to what we've seen before. And you can take advantage of some of their special chemistry. Rainy nickel would not reduce an acetal, but if you have a thioacetal, it will reduce that. And so you end up getting just these alkanes. This is one way to take a ketone off of a molecule. Treat it with a dithiol and followed by rainy nickel.